Okay, everyone, can you see this slide? We are on the first page.
Yes.
You can see this clearly, right? Okay. Now, I don't know what is this. Let me just move this. Okay. So, Assalamualaikum. Good morning, everyone. Oh, by the way, let me check the door first. Okay, so this is lecture 2. We are going to introduce you to the coordination compounds, how to name coordination compounds, the most common molecular geometry that you commonly find for coordination compound, okay? And a few other things that you are familiar with, okay, the oxidation states and everything. It's just that we are going to dive a bit deeper where the molecular structure is going to be a bit different, okay, and the naming, the nomenclature of the compound is going to be much longer than the one that you usually see. So can anyone here just give me one example of any inorganic compound that you know? Any? Any inorganic compound that you know?
It's me, Doctor.
Yes, what's your name?
Nurul Emilia.
Okay, Nurul Emilia, yes. An example?
Sodium chloride.
Yes, sodium chloride is one of the inorganic compounds that is commonly found in, everywhere, okay? So sodium chloride is simple, okay? Sodium chloride, what else? Potassium chloride. Potassium chloride usually used, you don't actually find it anywhere in your home. However, you can find it at home if someone is diagnosed with something that has to do with his heart, okay? So potassium chloride is used to make sure the heart is beating properly, okay? But anyway, the drug is not going to be given to the patient to be taken for a long time, okay? So anyway, those are simple salt, okay? Sodium chloride, sodium plus Cl minus, that's it. So for coordination compound, we also have salt, but they are a bit complex, okay, in the structure and the nomenclature. We still have the cation, we still have the anion, okay? So when you name sodium chloride, you spell it S-O-D-I-U-M, C-H-L-O-R-I-D-E. And there is a space, okay? You have to put a space between sodium and chloride, all right? So that will indicate ionic compound. This is the same thing gonna be applicable for coordination compound, okay? Nothing is new here except that the compound is a bit complex, that's it, okay? And the name of ligand is going to be quite pretty, okay? In a way that you don't actually come across this kind of ligand, okay? But since some of you have started doing your lab, your practical, you have come across acetal-acetone. Acetal-acetone is one kind of a chelating agent because there are two oxygens there, okay? That is very likely to form coordination with most transition elements, all right? Okay, okay, this is the right slide. So coordination number. In sodium chloride, we don't have coordination number because it's ionic, it's purely ionic, just sodium ion, chloride ion, that's it. There's no bond, there's no covalent bond, okay? So coordination number is actually the number of donor atoms. Donor atoms here means the ligand. The ligand, for example, acetal-acetone, okay? Acetal-acetone has two oxygen, right? So that oxygen, when coordinate to the metal, that oxygen is called the donor atom, all right? So it is the number of donor atom in the ligands that supplies the lone pairs of electrons to the metal ligand bond. Now, by reading this, you may get a bit confused, but actually what this sentence is telling you is that the number of bond that forms with the metal, okay, between metal and ligand, that's it, okay? So for example, if you have this zinc, okay, look at this example, that's zinc. Oh, okay, I forgot we have this pen here. Let me point. Okay, now you see, for example, you have a metal, okay, you have a metal, and then you have your, what is that? Eraser. Okay, let me get the pen again. Okay, we have oxygen. Okay, this oxygen is actually the oxygen from acetal-acetone. Okay, so this is acetal-acetone. It is actually a compound where this is delocalized. Okay, now when oxygen coordinates with metal, you see there are two bonds, right? So the coordination number here is 2. Okay, you don't look at the number of ligand. You look at the number of bond established between the metal and the donor atom of that ligand. Now, if you look at this example, there are how many ligands? Just one. There is just one ligand, but the donor atoms, there are 2 donor atoms. So each donor atoms donate electrons to the metal. Definitely, when you form a bond, you have to donate electrons, okay? So because of that, there are 2 bonds formed. So the coordination number is 2. Now, let's say you have another, what is happening with this acetal-acetone? Let's say you have another acetal-acetone, okay? You have another acetal-acetone here, okay? You have another one, right? Like this, okay? Then you have that blah, 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 all these delocalized, okay? And then there's another bond formed between metal and the second acetal-acetone. So how many coordination number is there? There are 4. Okay, there are 4 ligands. 2 ligands, yes. Anyone? I actually heard someone speaking. Do you have anything to say? No, okay. So there are 2 ligands, all right? If you have any questions, just raise your questions in the middle of the lecture, okay? It is fine. You don't have to wait until the lecture finish. So this metal, okay, this metal coordinates to 2 acetal-acetone. How many ligands? 2 ligands. How many coordination number? 4. Okay? Do you get this? Do you get these coordination number terms? Okay? So some metals like chromium-3 or cobalt-3, we say that most of the time, chromium-3, cobalt-3 will have the same coordination number, which is 6. So 6 coordination number actually makes an octahedral. Okay, because in an octahedral system, there are 6 bonds, 6 coordination bonds. So the coordination number is 6. Okay, but if the coordination number is 4, which means there are 4 donor atoms coordinating to the ligand, to the metal. Okay, so if there are 4 coordination number, the molecular geometry can be tetrahedral, can be a square planar. All right. If the coordination number is 5, that is a trigonal bipyramid. If the coordination number is 2, that is a linear. Okay, all right? Now, that will lead to the geometry. The coordination number will lead to the geometry. Okay, you know this. Okay, you already know this. So, the tetrahedral, octahedral, square planar, linear, okay, number of ligands, okay. Now, number of ligands, this, can anyone just justify what this means? When it is an octahedral, the number of ligands is 6. So how many coordination number is there?
6. 6
Six.
coordination number.
But you just wait there, okay? Is it true that when the coordination number is 6, the number of ligands is always 6?
No.
Why? That is correct, but why?
Because there could be a ligand that have 2 bonds, not necessarily should have just only one.
Yes, because some ligands are monodentate. And of course, there's only one donor atom. What if the ligand is like previously we have discussed acetyl acetone? Acetyl acetone itself is just one ligand having 2 donor atoms. So that will make the coordination number 6 if there are 3 ligands, 3 acetyl acetone. All right. So the number of ligand is not necessarily important to determine the number of coordination. The number of coordination is purely determined by how many donor atoms are there coordinating to the metal. Okay? You get this? Very good. Good. It's the same thing like trigonal bipyramid, tetrahedral, square planar, and everything. Okay? For a square planar system, it says here that on the slide, the number of ligand is 4. The number of ligand is 4. Is it necessary to be 4? Can it be any other number? Can it be 2? Can it be 3?
Yes.
Yes. Yes. Because some ligands are, it depends on the denticity, right? If the ligand is a monodentate, there's only one chelation site. That means there is only one coordination site. If the ligand is a bidentate, a tetradentate, a tridentate, pentadentate, so the denticity will increase. Okay? The coordination number will increase even though the number of ligand is just 1. All right? Do you all get this? Do you all really understand this? I'm going to give you complex structure for your training, okay, for your exercise, all right? You all really understand this? Okay? I hope you understand this. Oh, by the way, hybridization. You all have to remember this, yeah? I hope that you go and revise your principle of chemistry or inorganic 1. Hybridization. For octahedral, there's D2sp3, sp3, D2. For trigonal bipyramid, dsp3, blah, 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 down to linear. Now, we shall look into this later when we explain the various theory in coordination chemistry. All right? You have to remember all this. Okay, you can just go through this table on your own. Okay, there are examples of the linear geometry compound. Okay, like what is this? Diamine, silver. Diamine, argentum. Okay, silver is argentum. Then we have dicyano, copper. Okay, then we have, what is this? Tetracyano, zinc. And then we have tetraamine, cadmium. Then we have tetrachloroferric, tetrabromo, cobaltic. Okay, and so on and so forth. So from this lecture, you will be able to give nomenclature names to all these compounds, okay? Now, just like organic compound, okay, we have cation, we have anion, right? The inorganic as well also have anion, cation, and neutral compound. Now, neutral compound has no charge. You know that very well. The cationic compound will have a positively charge. It can be +1, +2, +3, plus anything. The anionic compound will have a negative charge, and the charge can be -1, 2, 3, 4, 5. Anything depends on the oxidation state of the metal and the charge on the ligand. Okay, so the bonding between metal and ligand generally involve formal donation of one or more electrons. Now you know this very well. To form a bond, there must be donation of electrons from the ligand, okay, to the metal. Okay. All right. A neutral coordination compound will have no charge, okay, like what you see here. Okay, no charge. And complexes, metal complexes, okay, coordination compound, metal complexes are always written in a bracket. Okay, sometimes they don't write it in a bracket, but sometimes they do write it in a bracket. Okay, however, if you read some research article, they don't write it in a bracket, because whenever you have a metal there in the compound chemical formula, everyone knows that, chemists all knows that these are coordination compounds, right? Now, chemical formula. All of you are very, very familiar with chemical formula, especially the organic compound, right? But it's going to be the same thing as organic. There's a bit of disparities, okay? When writing chemical formula, when you write a chemical formula, you always start with the metal, okay? You start with the metal followed by the anionic ligand and followed by the neutral ligand. And in this example here, okay, nickel is the metal, okay? Chlorine is the anionic ligand, because chlorine can exist as chloride. That's why chlorine here is known as anionic. Any ligand that can exist as ion, they are anionic ligand, okay, because they can exist as an ion. Water, ammonia, phosphine, these are all neutral ligands. By themselves, they are not even ionic. Even coordination with any metal doesn't make them ionic. They maintain their neutrality. Okay, they are neutral ligands. So they carry no charge. All right. So these will come afterwards. Okay, water comes afterwards. Now, if let's say there are more than one anionic ligand, so we arrange them according to alphabetical order. And if there are more than one neutral ligand, we arrange their position in the chemical formula according to alphabetical order. And of course, there's a square bracket. We don't use a soft bracket. A square bracket indicates complex, metal complex, coordination compound, okay, not a soft bracket. A soft bracket is used to distinguish among ligands. For example, let's say we have this, okay. I just don't know why this happened, yeah. Okay. Let's say you have this. This is not the same as this. Okay, it is not the same. Can anyone here tell me what's the difference? That's why the soft bracket is important, to make sure that every ligand is grouped accordingly. Okay, they can be differentiated. They can be distinguished among other ligands. Can anyone here tell me what's the difference between these two? Ferrum H2, ferrum H bracket 2. Anyone? Of course, you know this. You actually have seen this before in your school, but the concept is there, but you don't actually see this example in school. Anyone? Anyone wants to try?
Hello, doctor.
Yes, what's your name, yeah?
Chiu.
Chu what?
Chiu Wenti.
Chu Weng Ting, yes.
For the first one, the hydrogen is bonded separately on the Fe. But
Okay.
for the bracket one, for the first one, the H2 is directly bonded to Fe. But for the second one, the H2 is bonded separately to the Fe.
Yes. The first one is this. Please ignore that spike, yeah? I don't know what actually happened here. Okay? This is the first one. The second one is this. They are different. The first one means both hydrogen attach equally, coordinate equally to iron. You see this in organometal topic later, yeah, in your third year. Anyway, it carries the same concept as you have seen in your school, yeah. Hydrogen in the first compound is a molecule, H2. Whereas hydrogen in the soft bracket is a hydride. That's why the coordination number remains 2. It's just that the type of ligand that coordinates are different. One coordinates with iron in the form of neutral hydrogen molecule. The other one coordinates to iron in the form of hydride. Okay? So this actually gives 2 coordination number. Okay? But we are not going to talk about this. I'm just giving you some advanced example. Okay? Just give you some head up to what is coordination compound is. Okay, anyone? Are you okay? Can you follow? Can you follow? Yeah, you can. Okay, now, nomenclature. Chemical formula is always written with the metal in front first, followed by the ligands. And among the ligands, we prioritize the anionic first, followed by the neutral ligand. Okay, that is clear. But when we write nomenclature, we spell it out. When you spell it out, you have to write the ligand. We have to write the ligand in alphabetical order, regardless of whether the ligand is anionic or neutral. Do you get this? Do you really get this? Okay? It is very important for you to understand that when writing the name, the nomenclature of the compound, you always write the ligand in alphabetical order, not in the order that you write for chemical formula. Okay, now, let's say we want to write about, this one here. Okay, this one. All right? So, the chemical formula arranges all these elements by putting the metal first and then the chlorine. Okay? The chlorine. Because it is anionic, followed by the neutral ligand, water. So, if you follow the chemical formula when writing nomenclature, you will put chlorine first, followed by aqua, then the metal. No. Okay. Look at these examples. Firstly, I would like to know, can anyone here tell me which is a cation, which is an anion? This example here. Which is the cation, which is the anion?
Blue one is anion. The red one is cation.
Yes. The red one is the cation. Cation is always in front. Okay, good. Now you get the concept. Cation is always in front. Okay, followed by the anion. Now, because cation is always in front, okay, when the metal is part of the cation substance, the metal will be named as it is: chromium, copper, argentum, aurum, cadmium, mercury, blah, blah, blah. Okay? Now, how many chlorine is there? 2. How many water? 4. Mono stands for 1. The prefix mono, okay? Mono stands for 1. Di stands for 2. Tri stands for 3. Tetra stands for 4. Penta for 5. Hexa for 6, and so on. Okay. So how many chlorine? 2. So dichloro. All right. How many water? 4. Tetra water. No, we don't say tetra water. In coordination compound, water as a ligand is named as aqua. Water as a ligand is named as aqua. We don't call it tetra water. Okay. So how many chlorine? 2. So dichloro and tetra aqua. Now, how do we arrange? Which comes first? We don't look at the alphabet on the prefix, tetra and di. Okay? We don't look at the alphabet of the prefix. We only look at the alphabet of the ligand. Aqua starts with A. Chloro starts with C. So aqua comes first, even though the prefix starts with T. Do you all get this?
Yes, doctor.
Okay, good. Okay, when you arrange the name of the ligand when writing nomenclature, you have to look at the alphabet of the first alphabet of the ligand, not the first alphabet of your prefix. Okay, so remember this. So that's why we put aqua first. It doesn't matter whether the prefix is a penta, a tetra, or whatever. Okay, so don't go with the prefix. So the name is going to be tetra aqua dichloro, chromium, because this red formula is a cation. Where it is a cation, the metal carries its original name. Chromium, okay, sodium, lithium, right, germanium, gallium, okay. No changes in the spelling of the name. And then after that, followed by the oxidation state. Okay, this is how you write the cationic part. The anionic is going to be the same way of naming sodium chloride. It's going to be chloride. Okay, no chloro. Why is it no chloro? Because this chlorine is not the donor atom, is not the ligand in the coordination sphere. This chlorine is anionic. So it carries the name chloride, not chloro. Okay? If water is the one that covering the outer sphere of the coordination compound, this will be named as hydrate. Now, why is water called aqua? Because water here is a ligand, a coordinating atom, okay, a donor atom. Now, example 2. Potassium is cation. Potassium is cation. So potassium comes first. All right, potassium comes first. The blue one is an anion. So what is the charge, the overall charge of the blue complex? Can anyone tell me?
-2.
Yes, it is -2. Okay, it is -2. You see, what you learn in school is actually applicable until now. It's just that the compound is getting a bit complex. That's it. Okay. Now, the charge is -2. You are correct. But how do you name it? Now, how many bromine is there? 4. Tetrabromo. Okay, tetrabromo. Do you see any other ligands with copper in the blue bracket? No other ligands. So there's only bromo. Okay, so tetrabromo. There is no need to arrange according the alphabetical order. Tetrabromo, ligand always come first. Okay, ligand always come first in the naming of compound. Now, if the metal belongs to the cationic, the metal carries the original name. If the metal belongs to the anionic, the metal here is copper, right? We call it cuprate. We don't call it copper or cuprum. We don't call it copper or cuprum. We call it cuprate. When you see cuprate, you know that this part is anionic and followed by the oxidation state. We have to mention the oxidation state of every metal. Okay? So when you see cuprate, you know this copper complex is a negative charge and anion. If you see copper or cuprum, that means this tetrabromo copper is a cation. Is everyone okay? Good? Good. Let's look at the this example here. This one here. Okay. Trichloro, triphenylphosphine, ruthenium. Okay. I want you to go home later. You study point number 2. Why is the name mer trichloro, triphenylphosphine, ruthenium 3? Okay. Okay, ligand. Some ligand by itself, okay, like dimethyl sulfoxide, urea, okay, dimethyl sulfoxide, urea, bipyridine, triphenylphosphine, by itself before coordination with other metals, with any metals, this is their names, okay, but they retain the name. The name will be maintained after coordination with compound. So neutral ligands are given same name as uncoordinated molecule. Before coordination, DMSO is called dimethyl sulfoxide. When dimethyl sulfoxide coordinate with a metal, it still retains the same name dimethyl sulfoxide. The same thing goes with urea, bipyridine, triphenylphosphine. But for ammonia, water, and nitrosyl, nitrogen monoxide, when ammonia, before coordination, the uncoordinated ammonia is called ammonia. When ammonia is coordinated to a metal, it is called amine. Okay? Water will be called aqua. Nitrogen monoxide will be called nitrosyl. Okay, you actually have done this. You are going to deal with ammonia here, okay, when you do your experiment in your 3rd year. Okay. Ligands that are anionic. Ligands that are anionic, okay, like chloride, bromide, hydroxide, fluoride, cyanide, nitride, amide, nitrate, carbonate, sulfate, acetate. When they are not coordinated, the uncoordinated version will be this, okay, acetate, sulfate, carbonate, all the 8. But the coordinated version will now remove the 8 and become ato. So acetate become acetato, sulfate becomes sulfato, carbonate become carbonato. Okay, not carbonara, but carbonato. Hydroxide becomes hydroxo. Bromide, chloride, fluoride, iodide becomes fluoro, chloro, bromo, iodo. Cyanide becomes cyano. Isothiocyanide becomes isothiocyanol. Okay, thiocyanide becomes thiocyano. Okay, all the O. All right, acetyl acetone becomes acetyl acetonato. So when you name your compound in your first experiment later, it will become tris acetyl acetonato, cobalt. I don't know, is it the cobalt 2 or cobalt 3? Okay, all right. But if the ligand is just a regular alkyl, it maintains the same name as in the uncoordinated version. Okay, methyl will just retain its same name. Ethyl, isopropyl. We don't call it isopropylo. We don't call it methylo, ethylo. Methyl remains as methyl, even in the uncoordinated or coordinated version. All right. This is the prefix that I mentioned earlier, the di, tri, tetra, and so on. This is to indicate the number of that particular ligand. If there are 5 chlorine in the coordination sphere coordinating to the metal, we don't call it 5-chloro, we call it pentachloro. Okay? But if let's say the ligand is already having that prefix, like triphenylphosphine, okay, when triphenylphosphine coordinates, and if there are 3 triphenylphosphine, it will become tris-triphenylphosphine. We don't call it tri-triphenylphosphine. Okay, we don't call it tri-triphenylphosphine. We call it tris-triphenylphosphine. Okay. So far, is everyone clear? Okay, everyone clear, yeah? Okay, metals. Okay, metals. If the metal belongs to the cation, okay, is within the cationic sphere, the metal remains its name. Okay, and if the metal belongs to the neutral coordination sphere, it also remains its name. The spelling remains the same. However, if the metal becomes negatively charged, I mean if the metal belongs to the anionic coordination sphere, the spelling will now become from scandium to scandate, copper to cuprate, ferrum to ferrate, manganese to manganate, nickel to nickelate, titanium titanate, aurum aurate, okay, argentum argentate, okay? Right? Okay, these are the examples, okay? You can find the oxidation state the same way you are taught in your high school and in your principle of chemistry, okay? The oxidation state of the metal is unknown. Water is a neutral molecule, so it carries no charge. Therefore, 6 times 0 is 0, equals to the overall charge of the complex is a +3. So that makes cobalt is a cobalt 3. So when you name this compound, cobalt now belongs to the cationic or the anionic? Can anyone tell me here? This cobalt, does it belong to the cationic or the anionic?
Cation.
Cationic. So the metal here cannot be cobaltite. It has to be cobalt, right? No cobaltite. Now, how do you name this? We start with the ligand. What is the ligand? Water. The ligand coordinates to metal, so it will be named as aqua. How many aqua? 6, so hexa aqua. Cobalt. Should it be cobaltite? No, because this cobalt is in the cationic sphere. Cobalt. What is the oxidation state? Upon calculation, we got it as +3. So it's a hexa aqua cobalt 3. What is the counter ion? Chloride. Okay. Now, if you look at this example here, bis-ethylene diamine, okay? Why is it called bis? Because there is already di in the name of the ligand. So when there's already a prefix in the ligand, di, the prefix for the whole ligand should be changed to bis, not di, okay? Can you tell me here how many coordination number in this complex?
6,
6. How many ligands?
4,
4. Yes. 2 chlorine. This is 1. Okay, this is 1. Ethylene diamine, ethylene diamine. So there are 2 ethylene diamine, 2 chlorine, so 4. Okay, it's not always a 6 coordination number, must come from 6 ligands. Okay, it has to come from 6 donor atom, not from 6 ligands. Do you understand this? But if all the ligands are a monodentate, yes, so 6 ligand gives 6 coordination, 6 donor atoms, so 6 coordination number. Okay. Now, this FAC mer, okay, this FAC here is facial. FAC here is facial. Meridonial. Mer is meridonial. Now, what is this? This actually, if you see facial and meridonial, you cannot draw the structure as you like. You have to draw the structure according to what is indicating here, facial and meridonial. Now, this will happen when there are 3 identical ligands that is positioned cis to each other. Okay, so in this example here, let's say we have a ligand. Okay, a ligand. This is the metal. Okay, I really don't know why is this coming up. Okay, so there is a metal. Okay, now cis position is always in an octahedral system. The cis position is always 90 degree to each other. Okay, so this axial, the vertical ligand is always 90 degree with the ligand, and always 90 degree. Yeah, I really don't know what happened here. Okay, it's always 90 degree. Okay, always 90 degree. So always 90 degree. When all these 3 ligands are 90 degree to each other, they are all cis to each other, you will name it as FAC, FAC, FAC. Okay, FAC, tri-aqua, tritoro, blah, 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 any name. If the ligand, there are 3 identical ligands, but, okay, one of them is trans to each other, okay, but they are cis to the other one. So that is a mer, that is a meridonial, okay, that is a meridonial. A meridonial will have at one trans, okay, one trans. So 2 ligands cis to this, okay, 2 ligands will be cis to the 3rd ligand. These will be trans to each other. When there is a trans and cis, that is a meridonial. Okay, so when you see FAC, facial means 3 identical ligands are positioned in a way that all of them are cis to each other, 90 degree to each other. When you see meridonial, it means that all the 3 identical ligands, okay, it has to be the same ligands, yeah? All the 3 identical ligands, 2 of them are cis to one of the ligand, and there's a trans. That's meridonial, okay? The rest will remain the same. Okay, so if you see this, you cannot draw the structure as you wish. Okay, this, all these are just actually indicator of how the structure is actually, okay? So when you see a lambda and a lambda here indicate that the chelating, this ligand is actually twisting anti-clockwise, and the delta is twisting clockwise. So if you are given a nomenclature where you see a delta or a lambda in the nomenclature, it shows that this ligand is going clockwise. You have to draw it clockwise, and this is drawn anti-clockwise. Okay, for bridging ligands, we always start with a mu. Okay, a mu here indicate bridging. Okay, and of course, it's going to be the same nomenclature, but this for nomenclature for bridging compound nomenclature, we will look at this later in our next lecture. Yeah, I have to go this slowly, but this is not so emphasized in the course. Anyway, for a bridging, we have a mu. Okay, you see the hydroxide is forming a bridge with 2 chromium. So you have a mu here, a mu followed by the ligand that forms a bridge, hydroxo. Hydroxide becomes hydroxo. Okay, hydroxo, how many hydroxo? 2. So mu dihydroxo. Bis. Why is there bis? Because every chromium coordinates to 4 ammonia. So there's already a prefix here, tetraamine chromium. And because there are 2 of them, so we don't put ditetraamine chromium. We put bis tetraamine chromium. Okay? And the oxidation state of chromium, right? Okay, you can do this on your own. Okay, anyone? Do you know what's the oxidation state of nickel tetracarbonyl here? Tetracarbonyl nickel. Carbon monoxide is a 0 oxidation state, a neutral ligand. So, is there any charge for this complex, overall charge? There is no charge. So, what is the oxidation state for nickel here? Anyone?
Zero.
Zero.
Yes, this is 0. Okay, so if you get a 0, don't ask me whether the question is wrong. It is not wrong, okay? And don't be surprised if when you calculate the oxidation state, some metal gives you a -1, okay? Yeah, there's nothing wrong with the question. So please do this, all right? Please do this. I would like you to try all this, okay? Then we will look at isomerism later in our next lecture. So please do this as your exercise. You can show me if you want me to check, okay? So the class ends. I'll see you on Monday. Monday we will have PTG, okay? So make sure you can log in to Edpuzzle. We are going to use the same platform, all right? Okay, class dismissed.
Doctor?
Thank you, doctor.
Thank you,
Thank you,
doctor.
doctor.
Thank you,
Thank you,
doctor.
Thank you,
doctor.
doctor.
Thank you, doctor.
Thank you,
Thank you, doctor. Thank you, doctor.
Doctor, how do we take our attendance today?
Good night.